Hello again. In the previous video, we showed how transistors are used to build logic gates for machine instructions in the CPU. The transistor symbol in the schematic diagrams shows how current flows. It does not really explain how a transistor works. That would require a more complicated explanation of electricity and physics. But here's the general idea. To the right of the standard transistor symbol is a simplified diagram showing the physical structure of a transistor made with silicon. Silicon is a semiconductor. Current does not flow through a semiconductor like pure silicon, but if other elements are added to the silicon, the electrical balance can be changed to a negative or positive bias, N or P in the diagram, so that current does flow. This transistor has 3 layers of silicon that have been treated so that there is a P layer in between the 2 N layers. The input current into the P layer changes the balance of electrons at the junctions with the N layers and controls whether current flows out or not, thus turning the switch on or off. Besides machine instructions, transistors are also used to make memory chips. Memory holds a binary value, 0 or 1, so a transistor in the off state is 0 and a transistor in the on state is 1. Memory chips are constructed out of large arrays of transistors that have circuitry to read and write to memory. Reading memory detects whether a transistor is on or off, and writing turns individual transistors on or off. In addition to functioning as a switch, another very important property of transistors is that they can be used to amplify a signal. A small input current can produce a higher output current. Transistors were a revolutionary invention. They were developed by a team at Bell Labs in 1947, and in 1956 the inventors were awarded the Nobel Prize in Physics. Transistors replaced vacuum tubes as amplifiers and switches in many applications, from radio, television, and audio equipment to telephone systems and computers. Compared to vacuum tubes, they were smaller, consumed less power, and were more reliable. They don't burn out like tubes. Transistors quickly became the basis for the modern electronics industry. But there was another great invention just around the corner. In 1958, a researcher at Texas Instruments demonstrated an integrated circuit in which many transistors and other electrical components are all fabricated on one piece of silicon, a silicon chip. Here's a picture of 4 integrated circuits, 4 memory chips that are mounted on a board that can be inserted into a slot in a computer. Below it is an Intel microprocessor chip with its cover removed. A microprocessor chip incorporates all the major functions of a CPU in a single integrated circuit. Compared to a printed circuit board, integrated circuits reduce assembly costs and greatly reduce size, so less power is needed and less heat is generated. The inventor of the integrated circuit was also awarded a Nobel Prize in Physics. It's hard to underrate the importance of these 2 inventions. Transistors and integrated circuits are considered by many to be the greatest inventions of the 20th century. They revolutionized the whole electronics industry. They paved the way for great advances in many areas and made it possible to create many new products. Personal computers, cell phones, and smartphones would not be possible without integrated circuits. If you're interested in learning more about the history of hardware, you can read Chapter 1 in the book, A Concise History of Computers, Smartphones, and the Internet, available free in several formats from a number of different locations. Designing and manufacturing a processor chip is a very large and expensive undertaking. Most computer and smartphone manufacturers do not design their own CPU chips, but buy them from third-party suppliers such as Intel, who have large semiconductor fabrication plants. These plants are extremely costly to build, around $10 billion each. The semiconductor industry is a very large competitive business with plants around the world and a total market of over $300 billion per year. Manufacturing a CPU chip is a multi-step process that may require more than 100 steps and take up to 30 days, a process that can cost several $1 million. First, pure silicon wafers are created from sand. Each wafer will contain hundreds of copies of the integrated circuit. This must be done in a clean room, as a slight impurity in the silicon may lead to failures in many of the individual chips. The design is built on the chip one layer after another. For each layer, a special film is first applied to the silicon. Then a mask produced by the engineering design software is transferred to the chip with a photographic process. Etching exposes the silicon in the light areas of the mask that represent the circuitry. Different elements are applied to exposed silicon, creating the NMP layers for the transistors in that layer. When all layers have been fabricated on the chip, an automated system tests each chip on the wafer. Those that fail are discarded. Finally, the wafer is cut into individual chips, which are assembled into hard plastic packages to protect the chip. This packaging is usually black and makes most silicon chips look similar. It's not possible to see any of the layers of the circuitry on the chip. The engineers in Silicon Valley have a mantra: smaller, faster, cheaper. Ever since the first integrated circuits were fabricated, the semiconductor industry has been able to make transistors smaller and smaller. As electronic circuits are made smaller, they get faster, since the electrical signals have a shorter distance to travel. In addition, more functions can be put on a single chip, making it possible to build smaller and cheaper electronic devices and computers. In 1965, Gordon Moore, an engineer who co-founded Intel, predicted that the number of transistors on integrated circuits would double about every 2 years. This prediction turned out to be quite accurate for both memory chips and processor chips, and is called Moore's Law. This is exponential growth, as you can see on these charts. The first integrated circuits had less than 20 transistors, but by 1990 there were about 2 million transistors on a chip, and by 2015 there were chips with 10 billion transistors. A laptop computer in 2015 compared to a computer 50 years earlier, a mainframe computer, since that was the only type of computer in 1965, was orders of magnitude smaller, faster, and cheaper. Moore's Law, more than anything else, has been the engine that has powered the huge advances in the computer and electronics industry. However, there is a physical limit as to how small the transistors in an integrated circuit can become. Transistors are now approaching the size where quantum physics will affect the movement of electrons, and transistors will not reliably switch on and off. Moore's Law will end around 2021, and that will be followed by a significant slowdown in computer hardware advances. There is ongoing research into alternatives to silicon for semiconductor manufacturing, and alternative computing techniques such as quantum computing, optical computing, and biochemical computing show promise. But it will probably be a long time before they will be ready for production use. So what have we learned about computer hardware? First, we learned that programs written in a computer programming language need to be compiled or translated into simpler machine instructions. Add EAX, 100 is an example of a machine instruction to add 100 to the number in the EAX register, which is one of the special components in the CPU. Second, we learned that machine instructions are designed with logic gates. This example showed how an add instruction can be designed by using an XOR gate with an AND gate. Third, we learned that logic gates can be built with simple switches. Transistors are used for electronic switches. This example shows how a basic AND gate can be built with 2 transistors. Finally, we saw how billions of transistors can be manufactured on a single integrated circuit or silicon chip in a semiconductor fabrication plant. That completes our explanation of the hardware side of computers. you now have the basic information to be able to design and build your own computer.